Okay, well, welcome back to our class on algorithms and data structure. We're making some good progress as we're working through these different data structure types, talking about bags, talking about stacks, talking about queues, talking about recursion, and then we have gotten into list. And so we gave an overview in the last lecture on lists, and now we're going to be talking about the implementation using arrays in this chapter. So we'll get into this. And so this is the listing of the textbook chapter contents. And so we'll look at using an array to implement the ADT list, and then the efficiency of using an array to implement the ADT list. So have you seen several examples of how to use the ADT list in a program? We will now discuss different ways that you can implement a list in Java. This chapter uses an array to represent the entries in a list. As in earlier implementations of other ADTs, when you use all of the space in an array, you can move the data to a larger array. Although we leave it as a project for, you could also use an instance of either of the Java classes array list or vector to represent the list entries. The result is likely using an array that can be expanded, since the underlying implementations of array lists and vectors use such an array. Finally, in the next chapter, maintains a list in a chain of linked nodes, because you can insert and remove entries at any position within a list. That the array-based and linked implementations are a bit more challenging than in an ADT implementation we have encountered previously. So let's talk about using an array to implement the ADT list. We began with the classroom analogy in chapter 2 to describe how an array can represent a bag. But this time we'll show how to represent a list. In doing so, we show how the add and remove methods would work. Subsequently, we represent a corresponding Java implementation for the list. So let's think in terms of an analogy. Let's recall the classroom A that was used in chapter 2. And we're shown in the figure here again. The desks in the room are numbered sequentially beginning with 0. An array is like this classroom, with each desk is like one element within the array. Again, we treat the classroom as a one-dimensional array and ignore that the desks are arranged in rows as in a typical classroom. So what about adding a new student alphabetically by name? So imagine that we have already a range of student in room A alphabetically by name. Suppose that a new student wants to join the students already in the room. Recall that 30 occupied desks are numbered sequentially from 1 to 30. Since 40 desks are in the room, the desk numbered 31 is available. When the students were arranged by arrival time, we would simply have assigned the new student to desk 31. Since the students are now arranged alphabetically by name, we must do more work. Suppose that the new student belongs between the two students who occupy desks 10 and 11. That is, the new student's name is alphabetically between the names of the two students who occupy desks 10 and 11. Since the desk positions are fixed, the new student must occupy desk 11 before the new student can be seated. The student currently in desk 11 needs to move to desk 12, as we're starting to show in the figure 11.2. This requires, however, causing a chain reaction. The student currently at desk 12 needs to be moving to 13, and so on. That is, each student seated in desk 11 through 30 must move to the next higher numbered desk. If only one student moves at a time, the students in desk 30 must move to desk 31 before the student at desk 29 can move to desk 30, and so on. As you can see, adding a new student requires moving several other students. However, we do not disturb the students seated in the desks that are before the new student's desk, desks 1 through 10 in our example. What about removing a student? Now imagine that a student at desk 5 of room A drops a course, the desks stay in a fixed location within the room. If we still want students to sit in consecutively numbered desks, several students will need to move. In fact, each student in desk number 6 and above must move to the next lower numbered desk, beginning with the student in desk 6. That is, if only one student moves at a time, the students in desk 6 must move to desk 5 before the student in desk 7 moves to desk 6, and so on. So here's an illustration using UML, the implementation. So the Java array-based implementation for the AD list incorporates some of the ideas that our classroom example illustrates. Our implementation is a class A list 1 that implements the interface list interface, which you saw in chapter 10. Each public method within the class corresponds to an ADT list operation. The private data fields are 1. Ordinarily, we would name the class array list, but as you saw in the previous chapter, Java already provides a class with that name, although we certainly could have named our class array list as well. We chose a different name to avoid confusion. So we have an array of objects, an integer that counts the numbers of entries in the list, an integer constant that defines the default capacity of the list, an integer constant that defines the maximum capacity of the list, a Boolean flag that indicates whether the list is properly initialized. And we can define the classes using the UML notation as shown here in the figure, where T represents the data type of the entries in the list. We have added the data field max capacity and integrity OK to assist with the class security, as we have done with other classes in previous chapters. So here is a listing. So the class A list has the form shown here. Notice that the overall organization of the class, the private data, and the constructors, we again use the class object when allocating the array, but must cast it to an array whose entries have the generic type T. Also notice the implementation of the first add method and the number 2 array. These two methods are our core methods, as we will use add to build a list and use to array to examine the list contents. We will provide implementations for other methods shortly. So just some more details as we're working through this list. Won't go through this in detail. Let's take a little bit of time to talk about the core methods that are included in this, because there's a variety of them, and so we'll have a little bit of a discussion here on that. So as we first mentioned, we have chosen to implement the first add method and the method to array before the others, as they are central or core to our class. Adding a new entry to the end of the list is easy. We simply add the entry to the array immediately after its last occurred location. Of course, adding a new entry is possible only if the array has available space. To guarantee this space for at least the first edition, just a second, sorry about that. The constructors now create lists whose capacity are at least default capacity. Following each addition, the add methods call the private methods ensure capacity to ensure the array if necessary. Thus, except for the point at which the array's capacity is checked, the first add method has an implementation much like the one you saw in segment 240 of chapter 2 for the class resizable bag array. Moreover, the definition of the ensure capacity, which appears at the end of the listing 11.1, as well as the definition of the method to array, are analogous to the corresponding methods in resizable array bag. In terms of a design decision, where should the method add call ensure capacity? The method that adds the entries to the array-based bag, and as defined earlier in the classes array bag and array stack given in chapters 2 and 6, respectively, ensure that the array has sufficient capacity before adding another entry to the array. Thus, the addition to the array might have to wait until a larger array has become available. However, if the addition fills the array will not be expanded until the next call to add. For this list, we take the opposite approach. We have chosen to verify the array's capacity by calling ensure capacity after the addition of another entry to the array. Because the constructors create sufficient space in the array for at least the first addition, we can enlarge the array as soon as the addition fills in. Thus, the array will always be ready to accept another entry. If, however, another addition does not occur, the array expansion will have been unnecessary. In our present context, the point at which you call ensure capacity is irrelevant. However, performing certain tasks at the same time or in parallel is possible and common with today's technology. By calling ensure capacity last, you can have the array expansion occur in the background as a separate thread. This allows add to return so the client can continue execution while the array is expanded. In this way, we ensure sufficient array capacity without delay for when the client needs to add an array. Creating a separate thread, however, is beyond our present scope. Okay, just a little bit more details as we're going through that list, and I'll just continue on from there. So let's talk about using an array to implement an ADT list. And so in this figure, we're showing how to make the room to insert Carla as the third entry in array. So this gets into the private method make room. The next study question asks you to implement the private method make room. In most cases, the method shifts list entries towards the end of the array, beginning with the last array, as in figure 10.11.4 illustrates. However, if given position is a number of entries plus one, the addition is at the end of the list, so no shift is necessary. In this case, make room should do nothing. What about adding to a list at a given position? The ADT list has another method that adds a new entry to a list, adding it at a position that the client specifies. Adding a new entry at an arbitrary position within the list is like adding a student to a room A in our example in segment 11.2. Although that example positions students alphabetically by their names, remember that the list client, not the list itself, sets the position of each entry. Thus, if that position is before the end of the list, we need to shift existing entries in the array to vacate the desired location so that it can accommodate the new entry. If the addition is to the end of the list, no such shift is necessary. In either case, space must be available in the array to accommodate a new entry. The implementation of add uses a private method make room to handle the details of moving data within an array. Remember that we can add to the list at positions that range from 1 to the length of the list plus 1, according to the specification given in segment 10.9 of the previous chapter. We must throw an exception if the given possession is invalid. So here we can also talk about the private method remove gap. And so the private method remove gap shifts the list entries within the array, as we're illustrating here in the figure, beginning with an entry after the one that is removed and continuing until the end of the list. Remove gap moves each entry to its next lower position. For the method remove, after thoroughly testing the two add methods in two array, we begin to define the remaining methods. Removing a list entry at an arbitrary position is like the response when a student leaves a room, A in our example in segment 11.3. We need to shift existing entries to avoid a gap in the array, except when removing the list last entry. The following implementation uses a private method remove gap to handle the details of moving entries within the array, like the method add remove is responsible for checking the validity of the given position. Note how this check also ensures that the list is not empty. We have the private method remove gap. The following private method remove gap shifts the entries from the array. And so here we're seeing the actual Java code for that. For the method contains, the method get entry locates the entry at the given position by going directly to the appropriate element. In contrast, the method contains is given an entry not its position, and it must search the array for the entry beginning at index 1. The method examines each array entry until it either locates a desired one or reaches the end of the list without success. And so in this implementation, we see the local Boolean variable to terminate the loop when we find the desired entry. Let's talk about the efficiency of using an array to implement the ADT list. Before we look at another implementation of the ADT list, let's examine the time complexity of some of the methods in our class A list. And so adding to the end of the list, let's begin with the operation that adds a new entry to the end of the list. So we can see this is the code for that, and as an efficiency, a big O1. If the list of entries is not full, each step in the method is an big O notation 1 operation. By applying our knowledge of the material presented in segments 416 and 417 of chapter 4, we can show that this method is big O1. If the array is not resized, that is, we can add an entry to the end of the list independently of other entries in the list. As we have seen in previous chapters, resize an array is a big O and operation. Thus, the method ensure capacity would require a big O and time if it encounters a full array. In this case, adding to the end of the list would be a big O and operation. If we continue to add to the end of the list, the operation would be big O1 again. So adding to a list at a given position, the second add method adds a new entry to the list at a client-defined specification. And we can remember what we talked about in segment 11.8 for that. So here is the last method that we'll talk about. This method differs from the previous add method because it usually calls a private method make room, whose definition appears in segment 11.9. To make room in the array for the new entry. The only time it does not call make room is when the addition is at the end of the list. After removing make room's assert statement and comments, we are left with the following code. And so just some more details there. All right, well, that's going to end it for this lecture. Thank you very much.